So thank you very much, everyone, to join today the Julia User Group Munich. I'm Stephan Sahm, and I today prepared a 101 introduction session on accelerating Python with Julia. I've prepared a couple of material. The first three are very basic, but the last is then really going into one demo case example where Julia is really compared to C++. Or one C++ implementation. Benchmarks are always kind of with a grain of salt, but still it's quite awesome to see. We're going to reach the same speedups as going the C++ way. So this is really great to have to grasp this. And yeah, so all these are Jupyter notebooks. So you are welcome to join hands-on and execute code yourself. Because we have a couple of material to cover, I'm not sure how much time there will be to kind of really get into a task and have time to solve kind of something. But I think that's still fine. So you can use this Jupyter notebook also afterwards just to get quickly into this topic again. Okay, so also one little excuse from my side. The last months have been a little silent. So I wasn't doing any extra Julia User Group Munich meetups. And this was mainly because of time issues, as I was launching the first product of my own company, Jolin. It's still not announced in the Julia community because it's really super alpha. But for you, I just wanted to say that was the main reason. And if you go to jolin.io, my company website, you find kind of some celebration here on the top, the Jolin Cloud. And if you're curious, just check it out. I'm very happy about everyone who likes to test it. So for those who know, it's kind of a deployment of Pluto. But yeah, as soon as the alpha stage is over, I'm also going to officially make an announcement in the Julia community to attract more people also here. So I think it's a cool thing, just that, you can take a look, and I'm very happy about everyone who likes to test it out. Okay, so then let's start right into it. So if you go to this GitHub page and click on the first link in our outline, what's going to open for you is a binder page. This now concretely is hosted on jesus.org. And yeah, and it should start super quickly. So this was for me. And yeah, so I hope it's similar for you. And I get a little information here on the top. Yeah, you can ignore that. Okay, so let's do it a bit larger for the recording. Yeah, so I want to, because this is kind of beginner's talk, but also kind of really focused on getting into Julia, I really want to compare the two approaches which are there currently. So yeah, you have two packages. It makes it a bit more complicated, but okay, yeah, this is just the landscape and we have to deal with it somehow. So there's the PyCall package, which is a bit older, and the Python call package. We're going to look into both. I've made a little table here on the top to summarize kind of the main parts, which sometimes always confused myself. And yeah, it might be kind of a good mental summary for you to just have a key takeaways. In general, we have now these 4 notebooks which I want to go through with you. So the first notebook which we're currently in is using the first part, the PyCall, and the opposite package from the PyCall is called PyJulia. So we are currently running in a Python kernel actually, and we now want to access Julia. So this is really the accelerating case. Later, we're also going to look at the other side to just access Python. I think for most kind of the acceleration case, kind of the one which is really, really interesting. To start with, we kind of set up some environment variables so that our PyCall is actually using this environment, which is here created for us. So this is a Jupyter running on Binder, and yeah, so packages are pre-compiled, and it would be nice to also reuse this. After having set this environment variable, we can use the package Julia. So this was also installed, and it's kind of a bit surprising, but yeah, so the package is called PyJulia, but it's on PyPy, it's available as Julia. So it's a little, yeah, it's a bit ambiguous how it's called. And yeah, so, but it suggests to be the standard. But you need to kind of get some little extra introduction, a little extra configuration so that it works in this binder setup, but nothing too fancy. And what we then do here in the last one is that we load Jupyter extension, which is called here julia.magic, so that we get access to some Julia helpers, yeah, with percent signs in front. So these are called magics in the Jupyter world. They are very handy to get just your hands on this interaction. Okay, just taking a look whether there are already some chat info. Not yet. Okay, so the Julia interpreter initialized would be the same for you if you're joining here in hands-on. So we're now just executing some random Python stuff. We have a little array, and now we just want to get this to Julia. And the first thing I want to show you here, and we're going to do the same with the Python call side, is the types, so that you get a feeling kind of what is actually going back and forth. And yeah, what we're doing here is that we execute code inside the Julia subprocess. So this is where this Julia magic comes in very handy. And actually, this Julia magic has a little extra magic if we use PyCall, which is also super nice. We can use this $sign to get Python variables inside Julia. So in Julia, we call this interpolation. And it's used kind of in many places along the language. But here it's also especially useful to kind of switch between the languages. So we see that this array is kind of coming from Julia, coming from Python, and we run it inside Julia. And what we do is here we print out the types, and we see the type kind of just as it arrives. And we see that it's not a Python thingy, but it's really converted for us, auto-converted for us to a standard Julia type. So this is really the standard Julia type of a vector of integers. And if we apply some functions, and here we use broadcasting, it's a nice thing in Julia for those who are new. With the dot, we can apply any functions to element-wise to an array. More concretely, it's using broadcasting. We see after applying this, we actually get a bit vector. This is just a compact representation of Boolean. It's odd or it's even. If we get this back to Python, so you see that the standard Julia now just here hasn't printed anything as a return. And as it is a kind of a code cell magic, we cannot return anything. But with only 1%, we can actually use it also as, to return something. And we just re-execute the same as odd, and we can kind of take a look at the type which comes back to the Python side. And this is the expected Python type. So the conversion is again done for us. And this is the flavor which this first package, this PyCall, gives to you. It really is meant to auto-convert things back and forth to the standard representation in Python or in Julia. So this makes it very easy to work with it. And and one example, which you will see is different if we use the other package, is also that we can use Boolean variables, Boolean values. And here I just make some stupid stuff, so I compare to the array element-wise to some value, and I use then numpy.any. So this one is actually even not a Python. No, this is even not a Python Boolean type. So if you look at it, this is actually special stuff. So NumPy has their own Boolean types, and this is actually a NumPy type. So there's a couple of confusion going on in this typing system, but because it's all auto-converted for us, it doesn't matter. We can go to Julia and get a standard if-else here, and it works. So this is really crucial because in if-else, the first argument definitely needs to be a Julia Boolean. If this is some fancy wrapper around a Python value, this would all break. but the conversion is done for us automatically. So what looks super intuitive here, is actually a feature. So this is this is what PyCall does for us. So that's the first part I want to show, and we later look into kind of the analogy on the Python call in the second package. And so as you see, kind of we have a true, and if we kind of get some false here, it also works. And this is kind of for beginners, it's a quite intuitive feel. Next, I want to go kind of a little bit more complicated, and I think for most of you, the data frames is just something which you use daily, and hence I also look into the data frames. So here in the beginning, I just have kind of a little stupid dummy example where we have some data frames from the Python side, and now I want to show you kind of how to get this onto the Julia side, and then possibly work on it. And so we can use this Julia magic. And here we use a little extra package, which is actually also called pandas with a capital P. So this, for this purpose of interacting between Python and Julia, this is really great. So someone made a really complete wrapper on the Julia side around the pandas data frame. And it's called pandas with a capital P. And the data frames package is the standard Julia data frames package. And we now can kind of wrap this one after another. And the pandas way, the pandas data frame now kind of has all the helper functionalities, so that finally we get actually a data frame. And then this is needed. So if you wouldn't use this intermediate pandas data frame here, then actually, it's not one of the supported cases. So the data frame is a custom type. It doesn't belong to these primitive simple types. So the PyCall does not come with a predefined way of converting this. So you would have to convert it yourself, use the constructors, and with the pandas as in between, we can really just use simple constructors because the pandas library already wraps everything. So this takes a bit longer, and probably also for you. And this is because of this binder setup, we need to turn off some pre-compilation features. And I guess now we spend time on pre-compiling. This is my best guess. But it should come back in a few seconds, I hope. What's interesting here? No, I think this is kind of very straightforward. There we are. Okay, so if I execute this a second time, it's there immediately. So this was really pre-compilation. What we see also here, which is going to be different than the Python call, is that we have a representation of the Julia side, but it looks like a little bit edgy. So it's not super smooth. You can work with it, you can understand what is there, but of course it would be nice to have kind of a similar lovely HTML version of it. So this is one downside of the current PyCall, which we are currently looking at. But okay, practically it's useful. So then I also want to show you the other way for completeness, because you may want to go the one or the other way. And now we construct a data frame on the Julia side, naming a data frame second, and getting something in. And so this is a quite complex little example. And as of now, it's just on the Julia side, and we would like to get it back to Python. So I have a JDataFrame2 here where I just access this variable. And what I now can do is just wrapping this into pandas data frame. So I'm again using the Julia pandas library, and this way it's now really just a standard Python pandas data frame. So this way it's quite simple and really kind of the very same. And we're using the Julia helper library pandas now to really get this way in both ways. So as you see, looking at the types, if we just take the Julia the plain Julia data frame, yeah, then this is going to appear at the Python side as a JL wrap, which is a generic wrapper. It doesn't help us too much. And if we get the pandas data frame of it, we already get really the correct type. So this is nothing different. This is just a standard pandas data frame. And it happens that we can work with this on both sides, on Python and on Julia. Okay, so here you see also the output. So there's some extra stuff going on. Yeah, we have the missing is converted to a none. One of the downsides of using pandas, I guess. Yeah, so the support for missing values is a little bit lacking here and there. With the new pandas versions, it's better, but as you see, it's still in there. And we have also this char type here, which is wrapped into a PyCall JLWrap, a generic one, because in Julia, the chars have a different representation. It's not just a string. This would show up as a string, but it's really its own type. And apparently, yeah, the wrapping so far does not handle this additionally, but it's wrapping them. Okay, so I've gave you one link here, just if you want to experiment a bit with this interaction, because this is actually one use case, so you can speed up Python pandas by using Julia data frames. And the data frames documentation has really a nice overview about which pandas syntax corresponds to which Julia syntax. And to admit, so I actually prefer the Julia syntax, especially as we see right here. Yeah, this logs, I always get confused. Yeah, I guess it's the same for others as well. And I find the Julia syntax here and there even more intuitive than the pandas one. But of course, the main benefit is then speed and flexibility. Okay, let me give a short check. Yeah, still no questions. So you're really welcome to ask questions. I understand it's very basic still, but anyway, so I'm really happy also to introduce some Julia, which looks a bit weird here and there. Yeah, so you're welcome. Okay, so last part of this introduction to the PyCall is to kind of understand that what we've now done with this Julia magic, we can also do in normal Python code. Because this is important, because if you have built a Python application, you won't build it in Jupyter. Jupyter is just your environment for experimentation. So these magics won't be available for you. And yeah, and we can do this similarly. And the way we do it, it's actually quite similar in both versions. We import the package main as JL, because in Julia, the main namespace is kind of the namespace where everything goes on. So now we have a Python variable representing our Julia namespace. And there's a special function here. It's called eval, and we can run arbitrary Julia code. Of course, this does not look as good any longer as before. Yeah. So, but for kind of a Python application, this works. And you can also outsource this into another file and then include the file. That's perfectly possible. So anyway, how we define this then, we can access this now via our JL. So we define things always on the main namespace, and we now name this JL to abbreviate and to save some time. And this works. So what does not work is unfortunately, yeah. So we just wrapped the broadcasting application because in Python we don't have the dot. If we apply this is-op to the array itself without our little wrapper, we get an error because it just is not made to work on array. So if we access kind of the first element, then it works. Yeah. So this is all fine. But in case kind of you want some broadcasting, this would be kind of the easy way to go. You define your custom helper function, and then from Python you call your custom helper function. Okay, and you again see that we get back a normal NumPy array. So we are in our familiar space and can use our familiar NumPy tools on whatever was returned here. Okay, so there's one pitfall, however, because we have auto conversion. Yeah, which helps us a lot here and there, yeah, because we get these niceties. Okay, it's really the type which we usually expect. But sometimes it's just not the right type because it was not pre-seen, or it's really just kind of a technical difficulty to get the right type in all cases. And one example is actually the data frame and pandas data frame combination. So while we can do this here in the Julia world, it's actually not working if we do this with this programmatic interface, because the types just mix up. So it looks like it's really the same, but it's not. This call to pandas data frame here, of course, knows that it's going back to Python and will apply some auto conversions, which then fail to be translated back. So this concretely will give back a Python pandas data frame, but this is then wrapped again in a normal JL wrap and sent to the data frame. And the data frame function does not know how to work with this generic wrapper. It really needs to get the specific wrapper, but this gets lost. This type information gets lost if we kind of go just the Python route. So yeah, this as a little warning that the auto conversion is very handy for many cases, but it also can fail you. And in this case, yeah, don't be afraid. This is kind of auto conversion. Yeah, in case, just go to the Julia side of things and you have then full control. Okay, so yeah, how to do this? You can again, yeah, this is what I just mentioned. You go to the Julia side, you define your specific wrapper, which just does what you want, and then you don't have to deal with the auto conversions in your way because you defined your helper functions to just do the thing. And here we again get our little dummy data frame. Okay, so this was part one, introduction to PyCall, to PyJulia, sorry, but PyJulia is part of the PyCall system. And next we go to kind of a very similar notebook and see the second interface. And you will see the differences. And my main purpose for doing it this way is that we can use the Jupyter magics. Yeah, so these are kind of very handy when using Python, because Python itself does not have this magic support. So Jupyter is kind of our friend. And you can then, if you want, kind of place them next to each other and get a better feeling. Okay, I can do in PyCall, I can do this, and then Python call, I can do that. In PyJulia, I can do this, and then in Julia call, I can do that. So that you can have these two worlds next to each other. Okay, so if there are no further questions, I would just go on. So you can click on this right away, the Julia call link, and it's going to open another binder, which, yeah, usually starts in a couple of seconds. Okay, I see one question. There's the question, any performance comparison between pure Julia and Python implemented one? Yeah, so good one. So we can do kind of performance comparisons. And I did this in another session. So in general, you get performance benefits. Actually, if you're here and you want, we can kind of use standard time, I think. Yeah. Let me give you kind of a small example so that you get the feeling what it is about performance here. So the Julia word, let's again kind of get our simple array. Yeah, it's really small. And if we just do a simple multiplication times 2, we can time this because we are in Jupyter. Python has some helpers which in Julia are kind of just standard. And thankfully, kind of this combination is quite good. So we can time this also on the Julia side. And let's see, we of course need to use a little macro. And this was expected. Okay, so what happens is that we get kind of a it cannot deal with this interpolation. So this is one part which a bit above I mentioned in a comment. So this interpolation syntax is super handy, but it doesn't work well with these @signs, these macros, because they rewrite code. And yeah, as of now, they don't interact well. So we get this array kind of in a separate line, which also kind of, yeah, so we don't time the translation. And what we see here is a different, a different unit. It's a bit tough. Let me give you some better units. So this is the environment which you have doesn't come with the benchmark utils, benchmark tools. So I admit next time I'm going to include them. So if we use this benchmark tools, we have access to another macro, which is called btime. And we can do that.
If you have a local implementation, you can open in Julia, no problem with that.
So if I have a local implementation of what?
If you have a local implementation on your machine, Julia, we can just compare.
Yeah, sure. Yeah. I prefer to stay in here because this is kind of the environment where everyone else could also kind of follow. But I completely agree. So what we're going to see, we can already see this, yeah. So so this is faster actually. If I haven't done anything, yeah. So we are already there. Let's now have the benchmark time. So yeah, so you can install any packages you want in this environment, yeah. And yeah, and you see that we are actually kind of even a factor 20 faster. So now it's easier to see. This is nanoseconds, which 1 nanosecond is 1,000 microseconds. The other way around. 1 microsecond is 1,000 nanoseconds. And yeah, you see on this very tiny, super tiny example, yeah, we get an impressive speed up. So it's just kind of a little bit unimaginable. So you wouldn't guess that just multiplying an array by 2 can be something so difficult. And yeah, and this kind of shows you that Python has kind of a couple of edge cases, yeah, where you do small things and don't use kind of the APIs well. So we are mixing kind of some Python API with some NumPy API. Then it's actually not so fast. And yeah, on the Julia side, we have just the generic support. We don't need to, yeah, think so much about this performance side because in general we have quite performant code. And this is kind of one little example, and you get this kind of a couple of times. So if we increase now the size of the array, yeah, then Python will again be more nearer to Julia because the most time spent will be on the C++ part of the NumPy package. So the smaller, the more individual you get, the more performance benefits you get from the Julia. And I like this example very much because it shows that even on kind of stupid things where you wouldn't expect any difference, you actually see drastic improvements by switching to Julia. So really, if you have some individual code, then the performance increases you get by switching to Julia are usually enormous. I hope this answers the question, and thank you very much for the question.
Thanks.
Okay, perfect. So I think that was great. Great first part. So let's look into kind of the second package then. Meanwhile, also the environment loaded. So second part, again, same introduction, but now we are in the second step, and we are looking at the second side, the Python call side. And if we access Python call from Python, actually what we use is Julia call. So you're going to get used to these languages, but I think they are kind of intuitive. So from Python, we call Julia, hence it's called Julia call. We also have to set up some environment variables so that our Julia call picks up our setup. And yeah, and this works pretty well. So this is actually quite recent information I got from the package author of Julia call itself. The information of this one is really up to date. It's by today. And I think this is even not yet documented in the official documentation. but it's already there. And this is kind of the recommended way if you want Julia call to access some pre-existing Julia environment, then this is the way you go. Okay, so it looks very similar, as you see. Yeah, instead from Julia call import main from Julia import main SJL. Yeah, so this was before we've seen this. Yeah, we now have kind of the package Julia call, and it's very similar. And we also have kind of a magic extension, and here, yeah, we just load the package itself. And this is actually quite recent, so we're going to see kind of a couple of features which are really there just since the latest Julia call version, but they're very handy, and yeah, you don't want to miss them. So I probably already executed this one. So yeah, I follow the same style, yeah, so that to make as few noise as possible. So we can have our little array. And now comes already the difference. Yeah, we're going to look at the types. One thing is that in Julia call, this is kind of a downside if you want, but yeah, we don't have this interpolation syntax. We can't use the $sign to get things in, to pass things from the Python side to Julia. And this enables us to actually use macros totally easily, because everything which is inside here is standard Julia. There's no extra handling of variables. And the variables themselves, they are handled this way, that we add them as extra arguments to the multi-line Julia magic. And this is the feature which is actually really new since the latest version. And I like this a lot. So previously I made a little wrapper to get the variables to the other side. But with this kind of, yeah, it's easy for experimentation. So it's a different approach, definitely. You don't have this interpolation. You have more an explicit variable, a passing of variables. Yeah, but it has also kind of the advantage that you can safely use whatever Julia you want. And the show macro, as you see, kind of has the benefit that it prints what was executed in front. So this is kind of the benefit of macros. They have access to the syntax tree itself, so they can use just this information what you typed and output it, for example, here. And we see that I also executed the next cell, that the types are really quite different from what we've seen before. So if we pass an array from Python to Julia, we see that this is now a so-called pi array. So it's not kind of a standard Julia vector, but it's a specific type. And this one just wraps a NumPy array. So there's no data which is kind of transformed or copied, but it's just a pointer to the NumPy side. And this pi array has no functionality around it so that you can work with it like a normal array. If we apply our little function, whether it's even or odd the element, we see that we again get to the Julia side. So our pi array was kind of has an interface which our isOdd method or the broadcasting method understands, and the result is just a normal Julia response, like it would be if you imported a normal Julia array. So this is quite typical, that in a sense now we copied the data. Yeah. So the copying of the data usually happens sometime, and now it's just happened kind of one step later. And yeah. Of course, you can also think about whether you can reduce copying, but so now we only saved one copy step on the bringing stuff from Python to Julia, but still, if we kind of applied our thing, then we create, of course, a new vector, and this will be the standard Julia. Okay, so the example speaks for itself. So if we get this to Python again, just the very same like before. You see the syntax is similar, yeah. So we can have the single line Julia. We see that the result type is actually also not the standard NumPy vector, but a special wrapper. This is called here Julia call vector value. So this is again the same, but the other side around. So we have a Julia array, which is on the Julia side. And if we access this from Python, nothing is converted by default. You really just get a fancy wrapper which points to the Julia data. So you can work with this. And in most cases, it will kind of feel like a normal NumPy array. But actually, yeah, so you need to be cautious. There might be some edge cases where it's just not a normal NumPy array. And yeah, so this is a philosophical difference. Yeah, this Python call really has this design principle that nothing is auto-converted by default, and you have all these wrapper values. It has the benefit that if you go often back and forth, you don't need so many copy steps. But it has kind of also this downside that you need some more manual care, that you really have the right types. And yeah, one further example is again this little condition. And in Joule, if we use Python call, we need this PyTruth function. We cannot just simply refer to my condition because it's not auto-converted to Julia, but it's still a wrapper around some Python stuff. And we need to use a little extra helper, which is called PyTruth. And this will then give us the Julia one. So these kind of things you need to be cautious about because the auto conversion is just not done. And yeah, it's a different design principle. Okay, let's check. Is there some further question? Nope. Okay, so from the data frames part, also there are kind of some slight differences. And yeah, and the cool thing is that it's actually a bit simpler. So the one way does work automatically for us. So if we have this Python data frame and we get this to the Julia side, then yeah, actually we can just pass it directly. So we have this data frame here as to pass it from Python to Julia, and we can also inspect the type of it, and we see that it was handed over as a specific type. It's called a PyPandas data frame. So this is really an individual wrapper for the pandas case. So here we have to thank the developers of Python call to support the data frame case. And yeah, because the interface is clear now, this is all handled for us. We can just put it into the standard constructor and get our Julia data frame. So what's now really nice is that you see that this is actually HTML output. So this is I guess the main reason why I personally prefer Python call. It's that kind of a stupid reason, but yeah, I guess many others feel similar. So just to have this nice looking output gives me a feeling of being welcome and safe. And yeah, I like this. So you have really kind of great support for the output side. You even have kind of interactions if this get big. That really also the JavaScript part is there, so that you can expand columns and all this. So they did a lot of care for this plotting and displaying part. Okay, so if we go the other way around, we have some Julia data frame and want to get it to Python. Again, same example. We have one extra step in between. So there's a special function called PyTable. And yeah, and this is really to bridge this gap so that a standard Julia data frame can be interpreted by the Python side. And yeah, this is just good to know. So it took actually quite a while for myself to find this. And yeah, and I don't want that you need to look for ages to find this function, because data frames are just so common. It's good for you to know that there is this PyTable wrapper, which helps you for the other side to get something from Julia to Python. Okay, so I hope you've seen kind of that they are actually quite similar, but really have different design principles. So there's a reason why there are two different packages to interact between Python and Julia. So one reason is definitely that Python is so famous. So there's just enough market share to have two packages. But the other side is then really that you can kind of approach this foreign function interface in the manner of auto conversion, which helps you in a couple of cases, or kind of a manner of just wrapping things. And yeah, and they have both advantages and disadvantages. But I also hope that you've seen like they have roughly feature parity. We're going to now look at the other side of things. now we're going to get a Julia kernel and call Python. And also there we can kind of translate the one to the other. And yeah, so I think kind of to start with, because of this really good support for displaying, I recommend kind of this one, what we're currently looking at, the Julia call side. And it also has a couple of performance improvements here and there because it's just wrapping it. But they might be really negligible for whatever you're doing. So if you prefer the auto conversion, if this is your style, then go for PyCall. It's definitely at least as stable. PyCall is longer there. It's a bit more stable in the sense. Both options are quite strong. Okay, so then I would go to the third part, but I also need to be cautious about the time. Let me take a look. Yeah, we have kind of half of our session done. And I think I'm happy to give you kind of the last tiny intro. So this is kind of the opposite side of things, to really compare the two packages if you start in Julia and want to access Python. Okay, let me look. Okay, no further questions. Okay, so again, clicking off this very link will spawn a binder notebook. I'm so happy about this binder infrastructure. It's really simplifying hands-on material. And yeah, and there we are. Again, same overview. And now we're going the Julia version. So we are starting with the Julia kernel. It's already there. And I'm starting here actually with some helpers. So I'm using hypertext literal to do some HTML stuff, and already using it in the next line. I have a little show plotly helper, which takes a figure, a plotly figure, and writes this to a temporary directory. So for those, so we are now in Julia. Yeah. So for those new to Julia, this is now more the new zone. And yeah, in general, it looks very, very similar. Yeah. And here we kind of have just some simple function definition. And we have here, this is, I think, the most special syntax, comes from Ruby, and or maybe there's even some language before Ruby. And this do syntax creates an anonymous function. So I have a function getting a temporary directory name and doing something here. And then this function is inserted here as the first argument. So this is what this do does. There was a very short one, but I always have the feeling that this do syntax may confuse people. So yeah, so that you have at least some idea what it's doing. It's really nothing fancy. It's just an easier way to write such larger anonymous functions and saves us some brackets. So what we do with this temporary directory is that we write a figure to an HTML file and then read it out immediately and put it into an iframe. So this is some HTML magic so that we can just visualize plotly, which is generated from the Python side. So this is a real simple example. And so what I'm doing here is to set up PyCall again to use the setup. It's a bit more complex because I developed this locally and I wanted to have it work in both versions. But we, in general, in this environment, we just set it to Python 3, standard Python. And and we import PyCall now. So this is the opposite of the PyJulia. And if you would, this is kind of a bit Julia specific. If we would have used using PyCall instead, then many variables come into our namespace, which simplifies the work if you just use one of these packages. But because they are very similar, I don't want to have the namespace cluttered with the names which are so similar. And I just use the import, which now does not auto import any names into my namespace. Instead, I'm importing a special PyString macro. This is the one which I actually really like. We're going to see this. You may already know this. So if we are in Julia, we can access Python stuff in this PyCall way by importing the Python packages. And then we have a Julia object, in this case, pandas, yeah, which just refers to the pandas part. And we can assign attributes, yeah. So now I want the plotly backend to have a little mini example of a plot. And I'm creating a pandas data frame. So this is now really, it looks like normal Julia code, yeah. It just works seamlessly because we are using PyCall. The auto conversion is done for us, yeah. So we are just parting in a standard Julia dictionary and things work. And now we use the, this is kind of a pandas data frame, and we use that plot method, and we have our little helper now, which gets the output to us. So this is a little iframe, and yeah, and we have kind of some fancy plotly. So this works seamlessly. Yeah, and because this works so easily, just let's move on. Yeah, what is awesome about PyCall, and I like this really a lot, is that you have this interpolation syntax. We already seen there are some limits to it, so it doesn't work well with macros, but that's usually fine. You just define kind of, yeah, you separate the interpolation with the macros, and often this works out quite well. And yeah, and also from the Julia side, we have this interpolation. And as Julia is a little bit more powerful from what it allows as a language, it has this meta programming facilities. We now don't need any Jupyter magics, but this is just normal standard Julia. And we have this Py string. And what's important is actually, but in Julia, this has a very special name if you import it. So just, so this is Py, yeah, and we write it in front of this multi-line string. And this is really this one. So yeah, sometimes a bit confusing, even for me who is using Julia for more than 5 years. Yeah, so this is a macro, and it's a string macro, and they just have this, yeah, suffix. Very, very special Julia case. And we can now just get in our pandas data frame, yeah, and get just normal Python syntax and apply standard NumPy, and again access our pandas data frame with this interpolation syntax, and this works. And with this line, we now kind of created a sinus column. But what is kind of important is that you see that there's nothing returned. It's a little downside. I actually dislike this. I would love to see this kind of also returning the last value. But nothing like this. Yeah, so if you put in a 1, nothing is returned here. So multi-line in this setup always means nothing is returned. And if we go single line, then actually, yeah, we get the return value. And here we used the same. Now I just use kind of some selection, some with the Boolean vector, and then have kind of a subset. And we can also plot kind of also our sine curve. So we see our extra column, which we just added. So this works seamlessly. And we can also plot it again just to have another nice plot. And yeah, so nothing really to be interpreted here, but you see that it works. Okay, so personally, I'm a fan of this macro. I like this. It's super powerful, very intuitive. So with this interpolation, you have the same like on the, with this Julia magic, just the reverse. You can really kind of get things from Julia to Python super easily by just using this $sign. And yeah, and you can have a guarantee that you're really using also Python syntax. So this is nice. This is just Python syntax with some variables being interpolated. So you can also be sure this is really the Python syntax which you want to have, which sometimes kind of might be kind of a question mark. Okay, I'm using Julia. Is this really doing the same as Python? With this, you have the guarantee. This is Python syntax which is interpreted here. I like this. Okay, so I'm going to show you the other side, Python call, and again another check for some questions. No for questions. So here it's similar and kind of a nice little extra. So this is also why it's in one notebook. There's actually the possibility to now have both packages at the same time. Yeah, so this is the very same Julia process. And we've now set up the Py call and the Python call. And with this little extra here, they are actually also speaking to the very same Python process. So yeah, they're not two things being created, but really the same Python is reused. And we're doing a very similar setup. So I'm importing the package itself, and I'm importing one of its key helpers, which you're going to use a lot if you use the Python call version. So again, remember, while what we've seen above, their auto-conversion helps us. Yeah, but in the Python call world, nothing is auto-converted. There things are wrapped. And hence we're going to see that we need to be a bit more careful about manually annotating types. So the Py macro comes in already handy even but for importing stuff. So what also surprises me as an experienced Julia programmer, so this apparently is valid Julia code. Otherwise, the macro wouldn't be allowed to parse it. But as you see, it's kind of really Python code from semantics. So we import pandas now as pandas2 because we have the other pandas above. And we can again use it and assign the backend. Now I assign matplotlib as a backend because Python call actually has nice plotting support, nice display support, and I want you to see this. Okay, so now comes the creation of a data frame from a dictionary. And unfortunately, this is a bit more complicated. And this is because there are now auto conversions happening for us. And the data frame constructor on the pandas side really expects a standard Python dictionary. Yeah, it's not enough to have something which looks similar to a Python dictionary, but it's really somehow bind to the standard Python dictionary. And this is the way you can do this. Yeah, it's just also interesting that you see it. So there's a Py built-ins, which gives you access to the standard namespace. And we just call the dict wrapper now around our Julia dictionary. And this is, of course, a supported case. Yeah, this makes sense. So the Python call developers, they, of course, made sure that however they're going to wrap a Julia dictionary, it needs to be understood by a Python dictionary. So this way, we are now constructing the correct type on the Python side, and then the data frame constructor also works. But yeah, this is kind of the downside of the Python call part. You need to be explicit about these conversions because they are not done for you automatically. And it happens from time to time that it's not enough to have something similar, but you really need to have a Python dictionary. Okay, so we can also use again the plot library, so it looks very similar. And yeah, this is now it's a pandas thing. If we use the matplotlib backend, then this will return an axis. And yeah, for axis, there's no display support. We really need to get the figure. And yeah, this is why there's another dot figure here, which was not seen above for the plotly, because the plotly backend just handles differently. Yeah, so here you see kind of this really works seamlessly. Yeah, there's no hack around. You can use the standard backend, the standard plotting backend right away in your Jupyter. And yeah, this is kind of one of the cool things about Python call. Yeah, they have a bit more support for this plotting. I also want to show you kind of that you can also do this indexing. So actually this would work in this case without the Py. But from experience, I wasn't able to reproduce it on time. There are some situations where this indexing might kind of behave differently if you take a Julia semantics. And I definitely wanted to show you this and emphasize this. So if you just want to have kind of some Python semantics, yeah, and execute stuff, this macro is your friend. It will do all these conversions, yeah, which you usually need to do manually. It will do them automatically. So it's like an explicit auto conversion. And yeah, and this helps a lot. And it's especially good to know that this exists, because if you get into a specific error because some types don't match, oh, wow, you will search a lot. And hence, yeah, remember this. There's a little macro which helps you getting the types right. Because with this Python call part, the this conversion is kind of so important. Here are some extras. So the Python call has an explicit wrapper that you can use to get something to the Python side. So this example is taken from their official documentation. I think it's quite good, or at least adapted from there. So with a Julia string, you would not have access to a join method. Yeah, it's just not there. But if you get it to the Python world, then it's there. And as you would have guessed, yeah, using this Python macro gives you the very same benefit. Yeah, this conversion is done then automatically for you and looks much neater. And then finally, yeah, on the Julia side of things, you sometimes don't want to have these wrappers around Python objects, but you just want to have them converted to standard Julia stuff. Yeah, in this case, a string. And for this, there's a special method called PyConvert. I see there's some question. Let me print up. Can you give an example of using the best from both worlds, Julia and Python? Yeah, thank you for the question. So Julia gives you kind of flexibility to speed up things. Yeah. So if you have a large ecosystem of Python tools, then it may not make sense for you to switch to Julia. And this is actually, as of now, the case for most companies, for most applications. Yeah, they have an ecosystem of Python and of Python users, knowledge base around this, and hence it's kind of difficult to go fully Julia. And there you can use this kind of to really speed up your bottlenecks. It's also difficult to profile things accordingly in Python, but nevertheless, you may have kind of a good guess what is kind of the bottleneck. You can take this and improve it by getting just something quick to Julia. And you use exactly these interfaces. So there's nothing kind of extra fancy around it. Yeah, you don't need to compile the C library. You can if you want, but you don't need to. You can just use these interfaces. And as you've seen, they are very easy to get started. So it's something which Python users can easily do. So if they have the task to speed something up, then yeah, I would always suggest to try Julia because it's the quickest way. On the other side of things, yeah, where we are currently in this Julia process, the Julia kernel, Julia's biggest downside is the missing ecosystem. And also for migration, yeah, if you want to kind of go from Python to Julia, it might be that your specific package is just not yet in the Julia ecosystem, or not of that quality, or just not with this precise interface. Yeah, you really want to have this very interface. And then it's very handy that you can just include whatever Python you have. So this extends the ecosystem massively. And it's good to see that you can just reuse the Python world without much hassle. Yeah. So either with the PyString above or with this Py macro, you really get kind of a almost Pythonic feeling. Yeah. So there may be some edge cases, but for the majority of cases, the Julia syntax is so near to the Python syntax that you're relatively quickly familiar. And this is of course an advantage, so that you can really get the benefits of this Python world and get it into Julia. Performance-wise, yeah, okay, it's another thing, but it might not be that this is your bottleneck. Yeah, you create kind of some package, and it's totally enough for your use case to get kind of the slower Python version, but at least it works. So also here, I think there's a strong benefit of bridging these two worlds. Yeah, it's just a different motivation. You really have the motivation of getting access to the Python ecosystem. Okay, thank you for the question. I hope this was at least some answer. So finalizing this piece here, and then we go to kind of the final showcase, which has some benchmarks, is that I wanted to show you kind of, if you really love this the string version, yeah, then the Python call comes with the execute and the evaluate. However, they don't have the interpolation syntax. Yeah, so this is really a plain string, without the possibility to get things back and forth. So yeah, so you can execute this, yeah, and have a py function, and then you call the py function from Julia side. And calling is the way to get things from A to B, from Julia to Python. And yeah, so you can execute Python scripts with this. You just don't have this interpolation syntax, and the way you interpolate is by defining custom functions where you just pass your Julia variables, your Julia values as arguments. Thank you too. Okay, I was already saying that there's a lot of content today which I want to go through. This was very basic so far. I hope at least it was kind of giving you the appearance of being basic, because there's a lot of complexity which you need to take into account when speaking between two languages. And we see that we have two attempts for the same thing. So this already makes clear, okay, it's not straightforward what's kind of the solution. But I still hope that this introduction gave you the feeling, okay, this is kind of simple. We haven't looked so much into performance benchmarks, but be assured that, yeah, to get really high benefits. And we are now looking into one case, a bit more complex, so where it's really kind of, yeah, I would say a bit more realistic benchmark, yeah, so that you get the feeling, okay, we're doing something useful. We are not only comparing kind of a tiny method call here or there, and we don't know what this would be in a larger context. So this is now a larger context, still a dummy example, but yeah, I think it's good enough to give you the idea, okay, this is really worth it in terms of performance. So I clicked on the next link, and this will actually bring you to some completely different repository. I prepared this for this year's PyCon. So while the first 3 notebooks are in the repository, which I shared with you, this last one is in another repository, my PyCon workshop. But I think this is just perfect final one for our meetup today. So what we have here is a comparison of many different ways to accelerate Python. And this was also kind of my title of today's meetup, Accelerating Python. So what we compare is pure Python with some Python versions with C++ and Julia. So be invited to kind of check out the code in more detail. We probably will just kind of quickly go through it so that I explain it meanwhile. But as always, if you have some concrete questions, if you are some fuzzy questions, they are also very welcome. I'm happy to explain. So I start here with a little YouTube video. So because this is kind of, yeah, this is building on the work of a multi-agent guy. I actually have some high sound here. And the multi-agent AI guy, I'm very happy that he kind of built a C++ implementation and Python version. And what you see here is that it's just getting some little dots. I hope the resolution is high enough. So there are some dots which represent predators, and there are some dots which represent prey. And the predators, I guess, are the red ones, and they chase behind the white ones and eat them. And yeah, and then there are also some plants which are eaten by the prey. Sorry. And yeah, so the visualization is now super tiny. You don't see much, but still it gives you the idea of what is happening right now. So they move around, they chase behind each other, they have targets. So this is a super tiny biology simulation. And yeah, and this is kind of a perfect example for some individual computation, some individual model. And this we typically can represent and speed up very nicely using Julia. Okay, let's get into it. So I'm again using Julia call here. Don't be confused. Actually, the previous version had another .ipython here, and in the version today, it's really just loud extension Julia call. I haven't redefined this environment here, so I'm using the setup which I built for this year's PyCon in March. And yeah, and back then there was also not the support for this nice Julia magic. We're going to see it. I'm having a little helper set var, which sets some variables on the Julia side of things. And yeah, so I hope this is soon there. And we start with the word initialization. So we now kind of create this word in Python. Yeah, so this is completely self-contained, and we have some mathematics, some randomness, some dates. The date time we actually only use to place the seed for our randomness. So this is taken from the above linked blog post. So I adapted it slightly here and there, but most of it is taken from the blog post. And then I have some extra calls, because previous versions of the Python call didn't have this extra to get from Python to Julia side. I needed an extra little helper for that. Okay, so I hope we are there. First thing is not yet run, but it should be then second. Let's move on. So it's nothing fancy. We just set these constants. Yeah. So now we get into the Python agent, and we're going to re-implement this in Julia. So what it's done, it's initialized its agent. So this is all. It's maybe a plant, maybe a prey, maybe a predator. Yeah, all three. And there are some values: velocity, a world width and height, and also its position on the world, which gets initialized to some random position on the board. There's also some velocity here, so the x and the y, how fast it moves, and yeah, and we have also some extra helpers. It's still alive, it's a target of some predator, or no, it's the other way around. Whether this agent has a target, an age, it can get old, and also some energy if it eats stuff. This is a nice little dynamic. So we now we have an update logic of our agent, and we eat food. And every time we eat, we get older. That's kind of the downside. But if we eat something which is kind of good, we also increase our energy. So yeah, so this is kind of yeah, the basic idea. So we eat other targets. The other target is then kind of killed, but we get energy. And if we have enough energy, we're going to split. So there's a bit of code here, but I hope that this generic idea, yeah, is kind of giving you enough. So it's really not super fancy. As you see, we go through the lists. If we don't have a target, we search for a target. This is done here, and we move kind of forward, and yeah, we update ourselves into the direction. We have some Trägheit in German. What is this in English? Don't know. And yeah, and we update our own position. So it's really kind of a super basic way of simulating this. There's some code. And we have also a main method, which now defines here the predators, the prey, and plant. One nice thing about Python, we can actually define classes within methods. And yeah, we set them, they're identical, but the velocity, the maximal velocity is different. The predator is a bit faster than the prey. The plant can't move at all. Yeah, so I think this is quite realistic. The predator has a higher maximum speed. However, the prey are on average faster than the predator, because the predator only needs to catch the slowest prey. Okay, so we initialize this. We have some world width. We get a couple of preys and plants and so forth. And now we simulate. We have our while loop where we simulate. We let all preys eat. We let all predators eat. And we delete all the plants which are eaten. So the plants don't eat themselves, but they are spawned every time. And we also update our preys which are eaten, which are killed. And now comes kind of the nice thing. So if the energy is kind of enough for the preys, or the energy is enough for the predators, so there's some random threshold here, the prey will kind of split itself up into two new preys. If it has an energy of 5, and for the predators it's 10. So there's kind of really some reproduction going on, and then just some timestamp. And we're going to simulate this. Okay, so this is the basic simulation, and I like the feeling of it, that we have something kind of complex. Yeah, it's really kind of a concrete thing. We have implemented this in Python. We have used some NumPy here and there, but have we used NumPy? Good question. So we have mostly used kind of normal Python, but I think still kind of it's a good case because we're going to see the different speed ups. And yeah. Yeah, that's a good question. I'm not sure how much this relates to the current thing. So the question is, I think it's a good idea way to make a prototype and motivate to switch to Julia, since maintaining both will be a bit of work. What are your thoughts on this? So I think this is a kind of great invitation also to just chat a little bit in the chat. So if you have an opinion to this, feel invited to also just answer there. I'll come back to that. I'll finish this case to give you kind of some benchmarks, because also there was the question for it, and I think it's a good final one. But I'll come back to the question. So things are executed, and now comes also the first speed up. So what's the nice thing about Cython as a way to speed up Python is that you can actually build Cython classes which are perfectly compatible with the Python side. So we have now this Python agent defined above, and we have another pre-compiled agent which just added some type informations here and there, and then had a Cython agent. You can take a look into the code if you go to the repository. So then we can just time things. So for the Python thing, for the Python run, we need to reduce the number of runs, which by default is I think 10. So that things finish on time. And the Cython version, we can already run the normal amounts of time. And we're going to see some output. Okay, the output is printed here. So this is really the final one after the simulation. So we should only see 3, but if I remember correctly, we're going to see 4. So for someone who got the counting wrong. So if you specify a number of runs 3, then it's going to run 4 times. That's a bit cute. Okay, so what we see here is that we get a speed up by just using kind of some Cython agent. It also has, of course, a complexity. Now we have a Cython file here. We need to get this pre-compilation in, so it's not completely free, yeah. But you don't need to change a lot. Some CDEFs here and there, I'm not going to look into it. And we get a factor of 4, 5. Okay, so now we get a full language switch. The Cython version, which I have here in the background, also re-implemented this main loop. And we see that kind of if everything is in Cython, we get another speed up. Yeah, so now it's kind of a speed of a factor of 10. 500 milliseconds again, 5 seconds. So this is kind of the thing which most Python users easily do. They think about, okay, well, there was something like Cython, so let's try it. And you get some speed ups, which is kind of cool. So we have a good feedback. Now we kind of go to the C++ way. We first need to pre-compile it. So the C++ code, which is also here in the repository. And then we can time it with the Unix time command. And yeah, this is a bit, let me remember. So this is seconds, yeah. But it's still kind of, it's just a one little time. It was just to check. And now I'm using the sub-process run to really be able to time it a bit more statistically. And yeah, I timed it here on the Unix command line just to give you a feeling, okay, yeah, the times are kind of roughly correct. So what do we have here? We have a timing of actually 46 milliseconds, which is another factor of 10 compared to the Cython version. Yeah, so a total factor of 100 of the implementation. And yeah, just to make it right, we should see kind of also some timings which are in this area. Yeah, okay, so here we have a timing which is really only 17 milliseconds. Yeah, so I just want some way to confirm that the sub-process run is not adding kind of too much of an overhead and actually makes sense. So you see that in total, yeah, this is really kind of in total a factor of 100 faster. And we again have a couple of outputs, and because it's so fast, it just computed it several times. Okay, so the final piece now that I show you that the re-implementation in Julia is actually kind of meeting the same timings. So to really kind of have one demo case. And here I have kind of really some instructions. So yeah, we won't have time for that. But the original workshop at the PyCon had the task to delete the solution, which is going to be here, and rewrite it yourself. So how do we do this in Julia? In Julia, we don't have this type inheritance, but it turns out in this example also there was not much use of type inheritance. So it's super simple to rebuild the same. We have some agent which has all these variables, and we give type annotations. So this is now the thing which in Julia kind of you also do. You give type annotations, but they usually only are in this struct type. You only define the types on, let's say, your interface. Yeah, this agent is the interface. Some produce this agent, some consume this agent, and here we really kind of also in Julia typically use types. We can have generic types so that we infer them from the context, but still type information is quite essential in these objects. And Julia, we call them struct. And the predators and prey and plants, they are now just specific versions of this agent, yeah, where we set the Vmax. So in Julia, we have support for keyword arguments as well. And there you need to put a semicolon in front. And then everything after the semicolon is a keyword argument. Okay, so we have done this, and now there's kind of the update logic. In Julia, we separate the objects from the methods. So we have a separate update logic, which now implements the very same logic you've seen above. Yes, sometimes we need to get the type information on it, but it was actually complaining otherwise. But it's almost no type information. Yeah, if you take a look through it, it's really just more or less the same as in Python, even with the self. And yeah, and it's only this tiny piece here where I added some type information. And then we have this main loop, which also, again, does the same as in Python. We have also this for comprehension. So syntax is very similar. And yeah, and we use kind of then to speed up some things. We have this filter. If we would do for comprehensions here instead of a filter, yeah, just a little side note. This is indeed kind of less performant, but it turns out the C++ code we are comparing with, they also do in-place filtering. So this is a fair comparison. And yeah, otherwise it's kind of really the same. We are just adding some stuff to the predators. It's really more or less identical code, so to say. Yeah, now comes kind of the final part, so that we benchmark this. And yeah, we already saw the benchmark tools. The B time is the one which is just returning average time and allocations. And the second line, so you already see, we are executing this a couple of times. And I also made a second call. Okay, so it's done. And we have 13 milliseconds. And let's do this again to get a better feeling. So we have another call benchmark, which actually, yeah, has a nice plot somehow. And I have a little extra attribute which now gets away of these outputs. So the bottom line is that most of the time we actually are very low. Okay, so this one was not a good case. So here in this benchmarking part, we are now on 103 milliseconds on median. And yeah, we have kind of a couple of garbage collection taking place. This is also kind of what I wanted to highlight, because now the difference between Julia and C++ is really only the garbage collector. So if you kind of then take a look on what your garbage collector does, yeah, it sometimes, of course, makes things worse, but often it's actually better. And yeah, so yeah, if you take a look on this histogram, yeah, so the 14 milliseconds, if you use this benchmark time, it's actually kind of one of the best, yeah, where we are faster than the C++ implementation. And often we are kind of in the middle, often rather to the 100 milliseconds. So I hope you appreciated also this example to really kind of have one concrete case. I want to share this workshop also with you in the chat. So this is the link to the repository of the PyCon workshop, where also this links to. So if you like, take a look at the site and code, take a look at the C++ code. You can kind of inspect this and see that also from my personal opinion, the Julia version is the quickest to go. Yeah, so it's definitely worth trying it out. Then I have one question open, so thank you. I think this is a good idea way to make a prototype and motivate to switch to Julia, since maintaining both will be a bit of work. What are your thoughts on this? So from my practical perspective, yeah, it's good to make a prototype. This is kind of what several people also are happy to do with. But I really have this feedback that most are not happy to switch completely to Julia. So this is my personal experience. That yeah, for several reasons. Yeah, so if you're in the Python ecosystem, you're used to a very stable ecosystem. You have kind of strong packages, yeah, which are filling this need. So in this regard, I'm actually a bit surprised that there's now a new pandas implementation, Polar. This is a bit against this direction. So now we have 2 data frame implementations. It's rather unusual for Python. But yeah, usually you have kind of very stable packages where a lot of people got used to it. And yeah, and you don't want to miss this. And the Julia ecosystem as of now also has a couple of stable packages, yeah, which you can refer to. But in general, the Flare is more like getting really good peak performances. It's not so much about kind of getting really good baseline performances. I mean, still they are much better than Python, but I mean, so from the user perspective, yeah, you have a couple of specialized solutions. And what is really optimal is to get kind of the best performance you want. So Julia is built for high performance. But here and there, the packages kind of then lack some good defaults. Yeah, they may not be that good documented because they are kind of a couple of special cases. Yeah, it's not kind of really targeting the broad mass. And these are considerations which are important for teams, that you also have kind of a really good performance baseline. And yeah, and I think kind of, yeah, this is not the main target of Julia, but it's going to be improved definitely. So if Julia cannot increase the peak performance any longer because it's just too good on that, yeah, then definitely the focus of package developers will be to get really good defaults, to get auto mechanisms to approximate some parameters, yeah, to get easy and quick setups so that everyone can have a smooth, good experience even without going into the details. And yeah, and this is, yeah, there's kind of a conflict of interest. You cannot put your energy on all sides. But yeah, there I think Python is much stronger than Julia on getting kind of a really good baseline. And of course, just the reach Python has is so much larger, which is also a reason why people may not want to switch to Julia. It's just a smaller space of people who know the language, who feel already familiar with it. Julia is super simple. They get quick into it, but still without having tried it out, there's hesitation. And this is, of course, also important for teams. So I would wish I would answer like, yeah, this makes sense to just go pure Julia. But my personal taste on it, that it's just not the way the market is currently situated. So it's you will be forced to have a mixture of several languages, and and we all think that Julia has a strong case to be part of it, and it makes things easier to go pure Julia. But it's still very reasonable to have Julia just as a part. Then I wish you a lovely evening.